Hello, my name is Jordi Romeu from the Universitat Politècnica de Catalunya, and in this unit we'll talk about the electromagnetic spectrum and its applications. The first thing we'll talk about is just a few things about waves. What is a wave? Well, a wave is just an oscillation that travels through space, and we're able to transfer some energy, but with little mass transport, or actually nothing moving from one place to the other. So this is why I like to show this animation that just shows some sort of a wave. We have these little children just moving up and down, and we are able to cause that wave that propagates, but actually there is not a person that is moving from one place to the other. Waves are usually described by the wave equation, and of course, depending on the type of wave, we'll have different sort of description. Classical classification of waves, people talk about longitudinal waves, transverse waves. We have mechanical waves, but in our case, we're interested in talking about electromagnetic waves. Electromagnetic waves do not require a medium to propagate, and the important thing is that they can propagate through the vacuum. What sort of perturbation, or what are we propagating when we talk about an electromagnetic wave? Well, essentially an electric and a magnetic field. We'll see later on in the course that in order to exist in an electromagnetic wave, we have to have both an electric and a magnetic field that propagate. And when we say propagate, we mean that there is that disturbance or that change in the electric and magnetic field that is propagating in space. An electromagnetic wave in vacuum propagates at the speed of light. And as I said, we always have both the electric and the magnetic field. If we have a harmonic oscillation, we can look at the wave in two different ways. If we assume one fixed place in space, and we look at the evolution of the field as a function of time, we'll see this sort of oscillation. And of course, that gives us, and we measure that oscillation as the frequency of the wave. Another way to look at the wave is if we take like a snapshot and we look at the wave at a fixed time, and we see the distribution of the field along the distance. In that case, for a harmonic excitation, we also see this sort of sinusoidal variation, and in that case, one period is what we call the wavelength of the wave. Frequency and wavelength are related through the propagation speed. And they are inversed, so as the frequency increases, the wavelength diminishes, and when the frequency diminishes, the wavelength increases. Another important thing about electromagnetic waves is that the electric field and also the magnetic field have a vector. They have a vector characteristic. They are vectors. So when we describe the field, they have a vector characteristic, and for a field that has a harmonic variation, we can express a wave that is propagating along the z-axis as having two components, the x component and the y component. And its mathematical expression would have this form in which omega is the angular frequency and k is the wave number, each one of them related to the frequency and the wavelength. When we consider this sort of situation and we look at the evolution of the electric field in space, we can have different situations. We can talk about the linear polarization, and in that case, what we mean by linear polarization is that the electric field is always contained on a plane. From the mathematical expression, we can have linear polarization in different, we can have different mathematical expressions, either because the x component is 0, or maybe the y component is 0, or if we have both components, they are either in phase, so those values phi x and phi y are the same, or they are in opposite phase, so there is a phase shift of 180 degrees from one component and the other. In the case that the magnitude of both components, Ex and Ey, is the same, and they have a phase difference of 90 degrees, in that case we have circular polarization. That means that the E field vector describes a circle as it propagates. And in all the other cases, we will have elliptical polarization. It is important also to know that when we talk about a wave, an electromagnetic wave, we can describe it also, it can be described as a wave, but also as a particle. In that case, we talk about photon, and we know that, or that has been experimentally proved in many ways, but one of the ways is, for instance, through the photoelectric effect. In the photoelectric effect, electrons are emitted from solids, liquids or gases, when they absorb the energy coming from an incident wave. In that case, the energy of the incident wave is given by this expression, where h is Planck's constant and f is the frequency. So, the higher the frequency, the higher the energy of the photon. If that energy is large enough, we are able to have an electron being extracted, coming out from that material. In that case, we are saying that that wave, or that photon, is able to ionize the material. Now, in able to be able to ionize that material, we need a certain minimum energy, and that depends on the material, but that energy is, at least has to be of the order of 10 electron volts. If we relate that energy with the frequency or the wavelength, we find out that at least the wavelength of the electromagnetic waves has to be smaller than 124 nanometers. And that happens around the ultraviolet spectrum. Okay, so now that we already talked about the spectrum, frequency, and wavelength, we can put this chart. In this chart, what we are representing is the electromagnetic spectrum, and we are looking at it in different ways. Here, we are representing frequency in hertz. Here, the energy of the photons in electron volts, and up here, we have the wavelength in meters. So, we can see that as the frequency increases, 10 to the 6 will be 1 megahertz, and we are going all the way up to 10 to the 20. The wavelength decreases. That would be a wavelength of 1 kilometer, and we go all the way down to 10 to the minus 12 meters. We can see also that as the frequency increases, the energy of the photon increases. Then we can see the different bands that we're using. We have what we call radio waves, microwaves, infrared, the visible spectrum, ultraviolet, X-rays, and gamma rays. But although we are giving all these names, all of them share the same characteristic. They are all electromagnetic waves. And then, of course, we have different kinds of applications. For instance, in this lower part of the spectrum is where we have AM radio, FM radio, microwave ovens, radar. We know the applications of infrared, probably. We can use it to one things. We have visible, we have ultraviolet, X-rays, and gamma rays. And as I mentioned before, ionizing radiation, or ionization, happens at frequencies above the ultraviolet. So for most of our applications, which are in radar, microwaves, or radio, we are at frequencies that are far below they have an energy much lower than the one required to ionize matter. What are the applications? Well, we already talked a little bit about the applications of electromagnetic waves. Of course, in communications, we can have optical fiber, microwave links, satellite communications, mobile communications, broadcasting. All of them use electromagnetic waves at a frequency range that can span from frequencies around 1 megahertz, of course, until optical frequencies, because when we're using optical fibers, we're using optical frequencies. In remote sensing, either it's optical astronomy, radio astronomy, pollution control, radar, security applications, we are using electromagnetic waves to sense the environment, to obtain data from the environment, not just for communication. And then we have industrial applications that involve energy transmission, for instance, microwave ovens or laser cutting. And remember that when we talk about light, we're also talking about electromagnetic waves. When we talk about communications or a communication system, well, we can use the classical representation in which we have our source. That can be a microphone if you want to transmit voice, it can be a camera if you want to transmit video, whatever you may think of that. We have a transmitter, and now of course with that transmitter we have to do several things. We have to take the signal coming out from the transducer, we have usually to modulate it, we have to amplify it, so we can send it into the channel. And what is the channel? Well, the channel is our propagation medium, which can have several forms. It can be guided, if we're using a cable or an optical fiber, or it can be non-guided, if we're using antennas. And then, in reception, what we will have, well, probably we'll need an amplifier, we need a demodulator, and we'll finally need another transducer to have our signal back. So for instance, if we're transmitting voice, at the end, we need a loudspeaker to hear that voice. We will be concerned in this course a lot talking about this central part here, which has to do with the channel and how we transmit the information. And one very important thing to take into account is that in that channel there is always noise. That is, that in addition to the signal we want to transmit, there will always be some noise added to it. What are the sources of noise? Well, we have usually it's called multiplicative noise, that is, changes in the signal that are multiplying the signal we want to transmit, and some of them have to do with, for instance, changing the antenna properties, the antenna directionality, reflection in different areas, absorption, attenuation, or we can have additive noise, that is, things that are added to our signal. And one of the sources is thermal noise, also noise coming from the atmosphere or from the from the galaxy, or interference. That's signals, other signals that will be interfering our signal. So we have a usual propagation environment. Things are a little bit complex in a sense that we'll have, if we want to have, let's say, communication, satellite communication, but we'll see that we can have interference coming from another sources, we can have reflection in buildings, reflections in the ground, plus the noise added from different sources. What are those physical phenomena involved in propagation? Well, we'll have, as I said, reflection. But reflection usually assumes that we have a smooth surface. When we have a rough surface, we'll be talking about scattering. We'll have diffraction, and that is blocking caused by obstacles that interrupt the line of sight within the transmitter and the receiver antenna. We also have interference and atmospheric losses and other sources of interference. And what are the applications? Well, in applications, we have a whole range. When we talk about remote sensing, we make a usual distinction between passive remote sensing and active remote sensing. When we say passive remote sensing, we are considering sensors that measure natural reflected electromagnetic waves. That can be, for instance, a satellite, an optical satellite that actually takes optical images of the Earth, and we have as a source of illumination the sun. Or we are just measuring the spontaneous radiation of the bodies, and this is something we'll see a little bit in more detail in the course, and is that any body at a given temperature produces an spontaneous emission, and we can measure that emission and have and obtain properties of the body. Or else we have active systems. In that case, we have a system that is radiating, it's a source, it's radiating certain energy, and is measuring the energy that is reflected back, and from that we can obtain properties of the body we are examining. For instance, let me show an example of a passive system. This is some results of the SMOS satellite. This SMOS satellite is an observation satellite that measures sea salinity and soil moisture of the Earth, all based on the passive emission of the Earth. So here you can see a representation of the salinity of the soil of the ocean and how it changes through the year, and measured from this passive emission. If we make if we look in some more detail, we could see that also here in the ground we can see changes in the soil moisture, also due to seasonal changes. Another application of passive systems are due to security. This is an image of a person carrying, in that case, a toy gun underneath his clothes. And this is the image obtained measuring the spontaneous emission at 94 gigahertz. And because the emission of that metal part, which is that toy gun, and the body is different, we can see the contrast and we can obtain that image. We can have also active systems. In that case, we can use radar on a satellite to obtain images of the Earth with different applications. For instance, here you can see an application based on the use of which final goal is to obtain land use for a more efficient agricultural development. Here you can see an image of an oil spill in the Gulf of Mexico, and here you can see, for instance, the damages caused by the tsunami in Japan in 2011 from also a radar image. But also imaging systems based on electromagnetic waves, active systems, can have another application. This is, for instance, a simulation of a microwave imaging for breast cancer detection, in which an image is produced of the breast using several antennas that are illuminating the breast at microwave frequencies, and then obtaining an image. And because tumoral tissues have a different dielectric constant than healthy tissues, it is possible to obtain the position of those tumors from that images, with the advantage that in that case the radiation is non-ionizing as opposite to X-rays. If we go, for instance, also in active systems but at optical frequencies, we can have applications in communications using optical links to communicate satellites or satellites to ground station using optical links, with the advantage of having a very high, being able to support a very high capacity. Or we can use also active optical systems to, for instance, sense the atmosphere. And here you can see, for instance, a laser. You can see here the green beam pointing towards the atmosphere, and then how we can recover a profile of either clouds or the presence of pollutants in the atmosphere using this sort of measurements. So the range of applications that we have in using the electromagnetic spectrum is large, not only related to communications, and also remember that when we're talking about electromagnetic waves, we are not thinking only in radio, but we also have light and other parts of the spectrum.